Hi everybody. In this video we are going to go over Dijkstra's algorithm. So right here we have a weighted graph, and with Dijkstra's algorithm we start out with a list of vertices, and initially we only put in our starting vertex S into our list. And then what we do is we label the vertices like this. So S is 0 distance from itself, and a little dash there indicates it has no predecessor node. A and B are adjacent to S, and so we will label A as 3S, so that indicates it is of distance 3 from the starting vertex S, and B is distance 1 from S. Now the other vertices are not adjacent to anything in our list L, which is initially S, and so we will label them as if they're infinitely distant from S. And they will be updated. Okay, so that's our first step in Dijkstra's algorithm. And now what we do is we want to update L. And the way we update it is we look for the vertex that has the minimal distance associated with it. That would be vertex B. So that's of distance 1. All the others have a larger distance. So we'll add B to this list. So we'll just put B in there. And the next thing we have to do now is update our vertices, the labels on our vertices. And the way we do that is we just added B into L, so we look at all the vertices that are adjacent to B, and we will update their weights like this. So we look at A, it's adjacent to B. Now, what is smaller? The label we already have, which is 3, or if I take the label for B, which is 1, and add 1 to it because B is adjacent to A and that edge has weight 1, 1 plus 1 is 2, that's smaller than 3, so I will update this with 2 and A. So what that indicates is that it's actually shorter to go from A back to B and then to S, or from S to B to A in this direction, or this path, than going directly from S to A, which has a edge weight of 3. So it's shorter to go from S to B to A, because that only has a path weight of 1, or 2 rather, sorry, 2. Okay. Vertex D is adjacent to B, and so we can update this as follows. The distance from S to B is 1, and then from B to D is 2, so 1 plus 2, we can update this with a 3, and its predecessor vertex is B. Okay. And then we can update the C label. If we add 1 plus 3, that gives us 4, and the predecessor would be B again. And there we go, we've updated everything now. We've updated all the labels. Now we want to add another vertex to our list. So we look for the vertices that are not in L and have the smallest weight. So it looks like A is the smallest, that's not already in L, so we'll add A in there. And now we update the labels of all the vertices that are adjacent to A. Okay, so we look at D here. Now if I take 2 plus 4, that's 6, so I don't want to update D with a 6A because that's bigger than 3B. Okay, so it's shorter to go to get from S to D. It's shorter to go this way. It's shorter to go like this, then like this. Okay, so we leave that as 3b. Let's take a look down here. C is adjacent to A. So let's see, if I take 2 plus -1, that gives me 1. That's smaller than 4, so I want to update this with a 1a. So that tells us that to get from S to C, it's shorter to go like this. S to B to A to C, than going from S to B to C. You see, the 4 had us going SBC, that had a pathway to 4, but now we see it's actually shorter to go SBAC. And there we go, that's updated. And those are all, so we just updated D and C. Those were the vertices that were adjacent to A, and I think we're finished now. Now we continue adding vertices to L. So let's see. The vertex with the smallest weight or label that's not already in L, that's going to be C. So we put C in here. Okay. And now we update the labels of vertices that are adjacent to C. Okay, so let's see. Let's look at this one right here. D is adjacent to C. That has a label of 3. Now if I go 4 plus 1, that's not smaller than 3, so I don't want to change this. I want to leave this as 3b. E is adjacent to C, and 1 plus 2, well, that is definitely smaller than infinity, so I want to update this with a 1 plus 2 is going to be 3c. All right, and so we've updated all the labels for the vertices that are adjacent to C, and we are finished. Now we need to add another vertex to this list. So we look at the vertices that are not in this list and have the smallest label. Now that's only D and E. Now they both have the same label weight, so we'll just pick one arbitrarily, call it D. We'll just pick D. And then we look at we update the labels associated with vertices that are not in this list. Let's see, E is the only one that's not in the list, and it's adjacent to D. So let's see, if we went 3 plus 5, that would be 8, but that's bigger than 3C, so we don't want to do that. So we want to leave this as 3C, and that's it. So this tells us that to get from S to E, it's shorter to go through C than through D, because if we went through D, it would have a path weight of 8, but going through C, it has a path weight of 3. So we're finished, and then we add the only vertex that's not in our list here is, well, that's E, and so we put that in, and that's our final step, and we've got all of the vertices listed here, and we are finished. And so if we look at this, we can look at any vertex and it will tell us the minimal path to take from S to that vertex. For example, to get from S to E, the best path would be to go, we just sort of have to read this backwards, E to C, C to A to B, and then B to S. So the shortest path would be to go from S, B, A, C, E. So S, B, A, S to B to A to C to E. And if we add these up, we should get a weight of 3. Notice 1 plus 1 plus -1 plus 2, that is 3. And if we look at vertex D, it's the shortest path to get from S to D would be, we just have to read backwards here, we'd go from D to B, and then from B to S, and so that is the shortest path to go. So we'd go S, B, D to get to D. So if we add 1 plus 2, and that gives us 3. And there we go. So that is how you execute Dijkstra's algorithm. Let's take a look at one more example. So let's say our starting node here, we're going to label the A as S, so that's going to be our starting vertex. So let's see, down here we're going to have L starting out with S. Okay. And then let's see, so we're going to label these vertices D, we're going to label it as 9S. B is going to be 3S. C is going to be 5S. And then these are not, E and F are not adjacent to S, so we'll label them as infinity S and infinity S. Okay. Now we look for the vertex that has the smallest label. That's going to be B, so we throw that into our list L. And now we update our labels. So let's see, what's adjacent to B? C, E, and D, so we update those labels. Let's see, if I take 3 plus 3, that would give me 6, but that's not smaller than 5, so I leave this 5 alone there. D, if I go 3 plus 4, that's 7. That is smaller than 9, so I'm going to update this one with a 7B. Okay. E, yeah, that's, if I go 3 plus 7, that's 10, sorry, 10. And that is definitely smaller than infinity, so I will update this to be 10 and B. Okay. And F is not adjacent to B, so I don't look at that yet. Now we look for the label, or for the smallest label of a vertex that is not in this list. Let's see, that's going to be C. Okay, that has a 5 right here, so I'll throw C in there. Okay. And then we want to look at vertices that are adjacent to C and not in this list L. So let's see. D is adjacent to C. If I go 5 plus 2, that is 7. Well, that's the same as the 7 I already have here, so I'll just leave this alone. I'll leave it as 7B. I could label it as 7C. That would just give me an alternate path, but I'm just going to leave it as 7B. Let's see, E is adjacent to C, but if I go 5 plus 6, that's 11. That's bigger than 10, so I don't want to update this one with an 11C, because this is 10 is smaller, of course, than 11. Let's see, F is adjacent to C, and if I go 5 plus, I got to be careful here, it's 8. 5 plus 8, that's 13. That is definitely smaller than infinity, so 13 and C. And we're finished. We've updated all the vertices that were adjacent to C. Now, we look for we want to add a vertex in here with the smallest label. Let's see, so we've got to choose between D, E, and F. And the smallest one is D, so we're going to put a D in there. Now we update any vertices that are adjacent to D, update their labels. E is adjacent to D. If I go 7 plus 2, that's 9. That is smaller than 10, so I'm going to update this with a 9D. F is adjacent to D. 7 plus 2 is 9, and that is smaller than 13, so I'm going to update this with a 9D. And And there we go. We've updated all the vertices that are adjacent to D and not in L. So now we want to add into our list L the vertex not in L and has the smallest label. That's going to be, let's see, we've got E or F. They're both the same here, so we'll just add in E. And then let's see, we have to update the label for F possibly. So if I go 5 plus 9, that's 14. That is not smaller than this 9, so I don't want to update this 9. I don't want to update it with 14E because that would be bigger than 9, so I leave it as 9D. And then that's it. And then the last vertex to add in here is just the F. And we've got everything included in there now. S, B, C, D, E, F. And we are finished. And so now we can read off, for example, the smallest path from S to F. If we read backwards, it would be we go back to D, then from D to B, and then from B to S. So the smallest or shortest path would be S, B, D, F. And that would have a total distance of 9. If we add up 3 plus 4 plus 2, you see, we get 9. And there we go. Okay, so those are two examples there illustrating how to use Dijkstra's algorithm.